All right, so today we're going to start our new topic, new unit, talking about systems of equations. We're going to spend today just reviewing a system of two equations with two variables. And you saw this in Algebra 1, so we should not have to spend a lot of time on this, I'm hoping. You'll remember a lot from what we did back then. But we're going to solve system of linear equations by substitution and elimination. We're also going to talk about graphing method really quick. We're going to talk about why graphing is not exactly the best method in the world to use. And then we're going to take a look at some situations where a system of equations is necessary to model that situation and then be able to solve and answer some questions. So, first things first, what is a system of equations? Well, a system of equations is a set of two or more equations. Sometimes it becomes necessary to write more than one equation to model a given situation. As a matter of fact, if you're ever in a situation where there are two things you don't know, two things that you want to put a value to, but you don't know what those values are, you're going to need two equations in order to do that. As a matter of fact, the number of equations that you need is exactly the same as the number of things that you don't know that you want to have a value for. So it could be 2 or 3 or 4 or 5 or whatever. Now, when we talk about a solution of a system, it's the same as a solution for just an equation. Remember that a solution is any value that we can plug in for variables that would make a particular equation true. So, if we're looking for a solution to a system, like this system right here, then we're looking for a value of x and a value of y that we could plug in to make both of these equations true. It's got to make both of them true. Since we're looking for an x and a y, then what that means is we're looking for an ordered pair. We're looking for a point, basically. And so we start kind of getting into the idea of graphing these equations, right? You have to remember, why do we graph? Well, we graph an equation to show all the solutions for that particular equation. And so if we were to graph, say, this first equation, we would graph a line. It's a linear equation. And so there would be a bunch of points on that line that are solutions. If we were to graph the second equation, again, it's a linear equation, so we would graph a line. And there's a bunch of points on that line that would be solutions to that equation. So if we're looking for a solution, a point that makes both of those equations true, then it should be a point that's on both of those lines. In other words, we're looking for a point where the graph of the functions intersect. Okay? That's if we're graphing. Now, there are three different ways to solve a system of equations. You could graph them. Excuse me, like I said, if you graph them, you're looking for where those two graphs are going to intersect. But graphing is not a very good method. This suggests that you need to use graphing when both equations are in y equals mx plus b form. And you certainly can, but graphing is not very accurate. It's very difficult to do in any particular situation. And so what I would tell you is, even if the equations are in y equals mx plus b form or in slope-intercept form, I'm going to avoid graphing. The only time I'm going to use graphing is if I absolutely have to. If someone's going to make me use the graphing method, okay? So if graphing is not the best, then we've got two other methods, substitution and elimination. And there are some people who think that substitution is always easier to do. There are some that think elimination is always easier to do. I myself like elimination, and I'm going to try to do elimination anytime I can. I do agree with this in that you want to use substitution if one of your equations has already had a variable solved for it, like here, x equals 3y minus 5. I'm going to go ahead and use substitution because all I need to do now is substitute 3y minus 5 in for x and go solve for y. For me, other than that, I'm using elimination. Now, this says use elimination when all else fails. Now, I'm going to use elimination if I possibly can, if it makes any sense. If elimination starts to look too hard, then I'll start looking for these other methods to solve. But that's just me. Okay? So let's get into it. If we were to graph, there are three different situations that two linear equations might give us. One is if the two lines cross, if they intersect. We're going to look for one solution. The solution is going to be that point. And so this is an example of that. So there is some equation that if we were to graph would give us this blue line. Remember that the blue line indicates all the solutions for that particular equation. There's another equation where if we were to graph would give us this red line. Again, remember that that red line are all the solutions to that equation. And so if I need a solution that works for both, then I'm looking for where they intersect. Okay? In two lines, if they're going to intersect, most of the time they're going to intersect at one point. They're not going to intersect at 2 points because the line's not going to turn around and come back and intersect the other line again, right? So there's a situation where we might have one solution. Okay? There may be a situation where if we were to graph the two lines, they end up being the exact same line. Now they're intersecting at all of these points, right? All the points on this line are going to be a solution for both equations, and so they're going to be a solution for the system itself. Now lines go on forever, like they don't just stop right there at the end of that grid. This line would extend forever. So, when that happens, we're talking about having an infinite number of solutions. And so we say the solutions are infinitely many solutions, all the points on the line. Okay? That's if you're graphing. Now, the star over here tells us that if we're solving algebraically, if we're using the other two methods, substitution or elimination, then you're going to know that you're looking at infinitely many solutions if, while in that process of using substitution or elimination, you get down to something that looks like this. You get down to something that says 0 equals 0, or 5 equals 5, or -3 equals -3. Some equation, some sentence that is true, and that is true all the time, right? There are no variables in that equation, 0 equals 0, and we know that 0 equals 0 all the time. So that is the situation where you're going to be looking at infinitely many solutions. Okay. Now it could also be where, well, let's back up for a second. Even back up to where we have one solution. Yes, if we graph, we're going to be able to tell it has one solution pretty easily. If we're just looking at the two equations, the two functions. If we're looking at the two equations, we know we're going to be looking for one solution if they have different slopes. Right? So if I'm going to use the graphing method, then I'm going to put the two equations in slope-intercept form and then check out the slopes. If they're different, then I'm going to have one solution. Okay? Here, for infinitely many solutions, if we're looking at the equation form, y equals mx plus b, we're looking for, and we put the two equations in slope-intercept form, we're going to find out that they're going to have the same slope and the same y-intercept. That would make the two lines exactly the same, right? Sorry. And then it's possible that the two lines are never going to intersect, which would make them parallel. And if they're never going to intersect, then they're never going to have a point in common, which means that there's not going to be any points that work for both equations. And so that's a situation where we have no solution. And in equation form, we're looking for same slope different y-intercept. Okay? That way they're two different lines, but they still have the same slope. And so that'll make them parallel. Now, if we're solving algebraically, in other words, if we're using substitution or elimination, we're going to know that there's not going to be a solution to the system if we solve down and we eliminate all the variables add out to 0, and we're left with an equation that looks like this, like 0 equals 5, or -2 equals 10, or 10 equals 20, or whatever, right? If we get an equation that there are no more variables and it's still not true, then that means we're looking at no solution. I'm going to show you some examples of that, right? All right, so let's get to it. How to find solutions to a system. Here's a system of 2 equations, 2 unknowns, 2 variables, and here it suggests we need to solve by graphing. Now, in this particular problem myself, I would probably use substitution, because I would just substitute in for y, but they're making us solve by graphing. So all we got to do is graph the 2 lines and see where they intersect. So the first line, we go up to 3 on the y-axis. That's our y-intercept. Our slope is 4 over 1. So from here, we're going to go up 1, 2, 3, 4, over to the right 1. Or I can go down 1, 2, 3, 4, left 1. And I would go ahead and slope out the entire space and create as many points as I possibly can. Because I don't know where these 2 lines are going to intersect. I don't know if it's going to be a nice, pretty point or not. And I may not have a straight edge with me. So I can try to make a line as straight as possible. But if I slope out both lines, I may end up on the exact same point for both lines. I may land on the same point, and that would make finding the solution much, much easier. And here's what I mean. So for the other line, the y-intercept is -1. The slope is 2 over 1. So from there, we're going to go up 2, right 1, up 2, right 1. Keep sloping out, hoping that I land on a point on the other line. We're not going 2 that way. So now we go the other way. So instead of going up 2, right 1, we can go down 2, left 1, and down to, and if I do it again, there I'm landing on the a point on the other line. So that ends up being your solution. So your solution here is going to be -2, -5. Now, let me ask you this. What makes math so much better than any other subject in the building? Well, the answer to that question is you can always check your work, right? You can always check to make sure that -2, -5 actually is the solution. Yes, my 2 lines cross there, but maybe I messed up graphing. So what I can do is I can plug those 2 numbers in and make sure that it makes both of these equations true. So plugging in -5 for y and -2 for x gets us this. So we get -5 equals -5, and that's true. Here we get -5 equals 2 times -2 minus 1. So -5 equals -4 minus 1. So -5 equals -5. That's true as well. So -2, -5 must be the solution. Okay? You should always go and check your answers, check your work. Okay? Now, I'm not going to do that much more anymore in this video just to save time, but you need to go and check your work every time. When you get a solution, plug it into both equations and make sure that it works for both equations. Okay? All right, so again, just graphing 2 lines and finding out where they cross. Go ahead and take a shot at graphing number 2 here. Stop the video, graph it, then you can start it back up and make sure that you graphed it correctly, and we'll talk about the solution. Okay, did you get these 2 lines? Now, what does that mean? Well, it certainly looks like the 2 lines are not going to intersect. We can go over to the equation and find out that they do indeed have same slope, but different y-intercepts. So these guys are going to be parallel, so our solution is going to be no solution. There is no point that's going to work for both equations, right? So no solution here. Okay? Try 3 and see what you come up with for a solution there. Okay, did you get 2, 1? Hopefully you did. Okay, if not, come in, find me, we'll go through and figure out why not. Okay? All right, so that's graphing. Again, the graphing method I don't like. It's not very fun, it's not very accurate, it's not the best method. So we need to talk about some more methods. Substitution is the next one that I'll use. I'll use if it is the most convenient, but it's not my favorite. Elimination is, but substitution is handy if if you have your two equations, and one of your equations is already solved for one of the variables, okay? Because it's called substitution for a reason. And if we're talking about using substitution, that means we're probably going to substitute some stuff in, right? Well, we can only substitute in for a variable if we know what that variable is equal to. So in this particular equation, in the second equation here, we know that x is equal to negative 2y plus 2. No, it's not a number. It is an expression, but we can still substitute. If I know what x is equal to, I don't care what it's equal to, I can always substitute that in for x. And that's what we're going to do here. We're going to take negative 2y plus 2 and substitute in for that x right there. So we get 3 times negative 2y plus 2 plus 4y equals negative 4. Remember that we've got to take 3 times all of that expression, negative 2y plus 2. So we are going to have to use we are going to have to use distribution here. So distribute the 3. And then combine the like terms here. Subtract 6, divide by negative 2, and y is 5. Now, we know that y is equal to 5. That's the value for y that if we were to plug it into those two equations should help make the equations true. The problem is we don't know what x is, so we're not done. We're going to have to substitute again. And if it were me, I would substitute in for that y right there. It doesn't matter which equation you substitute in for, you can substitute in for either one. Right? And so we end up getting negative 10 plus 2, or x is negative 8. So it looks like our solution is negative 8 comma 5. Now, how would you know for sure? Yeah, substitute those in for x and y and make sure that it makes both equations true. Definitely do that. Okay? But that's your substitution. If you like substitution a lot and your two equations are not solved for a variable, then you'll have to do that. I'll give you a quick example of that in just a minute. Okay, there you go. Number 6, we're set up already. So go ahead and stop the video, use the substitution method, and start it back up and make sure you did it correctly. Okay, and there you go. There's your solution, 5 comma 1. You could, again, plug in 5 and 1, 5 for x, 1 for y, and make sure it makes both equations true. It is going to. But there you go. So I substituted the 3y plus 2 in for that x. Yes, both equations are solved for x. We know what x is equal to in both equations, but we're still going to use the substitution method, and it's the same. I'm going to take 3y plus 2 and put it in for x. So we get 3y plus 2 equals 7y minus 2, and then go through and solve for y. Once you got y, we got to plug that back into one of the two original equations and find out what x is. Okay? But there's your substitution. All right? Hopefully you got that. If not, make sure you come find me. Now, number 7. You don't have either one of your equations set up with one of the variables solved for. If you wanted to use substitution here, right? If you wanted to use substitution, you're well within your right, but I think it's going to be harder here. You could still do it. You'd have to solve one of the equations for one of the variables. And so I would have taken the first equation and solved it for x. And you get x equals 2y plus, we'll make this a decimal, 6.5. Then you could take 2y plus 6.5 and plug it in for that x. But it's a little bit more work, right? I don't want to use substitution here. Since I don't have one of my variables solved for, I'm going to use elimination. And so to use elimination, the first thing we got to do is make sure that everybody's lined up. The x's are lined up, the y's are lined up, and the constants are lined up, typically on the other side of the equal sign from the variables. And these guys aren't. Now, elimination suggests by its name that we're going to eliminate one of our variables. And the way we're going to do that is we're going to add the two equations together. And when I add the two equations, the only way I'm going to eliminate a variable is if one of those variables are opposites, if their coefficients are opposites. So if I don't have that already, we've got to use multiplication to make them opposites. And I kind of like to think about this like getting common denominators for a fraction, right? If I'm looking at these two as denominators, and I wanted to get a common denominator, that least common denominator would be 4, right? So I've got to use multiplication to make those two coefficients 4s. But they need to be opposites. One's got to be negative and one's got to be positive so they can add out to 0. If I wanted to do that for these guys, I'd be looking at least common denominator of 20. And so I'd make them each 20 using multiplication. Okay? It doesn't matter which variable you eliminate. You can eliminate x or y. You should get the same answer either way. So I tend to look at the ones that have smaller numbers so that I don't have to multiply by as big a number. And so I'm going to eliminate the x's. Now, I need to make these guys 4s, both of them 4, and this one already is. And I got to make one of them negative. So what I'm going to do is I'm going to multiply this top equation by -2. And notice that I multiply everything in that equation by -2. I have to do that to keep the equation the same, just looking different. So I'm going to get -4x plus 8y equals -26. Now, when I add the two equations together, these guys add to 0. And that's my goal. I want to eliminate one of those variables. We get 3y here and -18 here. And then we divide both sides by 3, and y is equal to -6. And now we're back to where we were with the substitution method. So there is a little bit of an element of substitution even in elimination. But now that I know that y is equal to -6, I've got to substitute that in so that I can find out what x is. So I'm going to take this -6 and substitute in for that y right there. Again, it doesn't matter which equation you use. To substitute the -6 in for, you just use whichever one you want. So we subtract 24 here, divide by 2, and our solution appears to be -11 over 2, common -6. Okay? Again, plug that into the equations, make sure that it works for both, and then you'll know for sure that that's your solution. But there you go, right? All right, number 8 looks like this. And so let's go through this together really quick, and then we'll get into our story problems. Now, pick one of the variables to eliminate. It doesn't matter which one, right? And if you look here, the x's need to have a common denominator of 2. One needs to be negative, one needs to be positive. The y's need a common denominator of 2, with one of them negative, one of them positive. So either one would be easy enough to set up and eliminate. I'm going to eliminate x, no particular reason, just because it's first. So I've got to make that coefficient a 2. In order to do that, I've got to multiply the entire equation by 2. So when we do, we get 2x minus 2y equals 6. When we do that, these guys add to 0, these guys add to 0, and those guys add to 0, so we get 0 equals 0. Remember what we talked about before, right? Does 0 equal 0? Yes, it does. Is it going to always equal? Are those two going to always equal? Yes, it is. That means whatever point I plug in, whatever point makes one of the equations true, it's going to automatically make the other equation true. In other words, this is a situation where we have infinitely many solutions. Okay? There are an infinite number of points that I can plug into both of those equations and make them true. Okay? Which also means that if I were to graph those two lines, they would be right on top of each other. They'd be the same line. Okay? Excuse me. It's when we're in the process of solving these equations that you get something silly like 0 equals 2, which is obviously not true. That is where we would get no solution. But here it's infinitely many. Okay? So I just wanted to throw that out there. And so there's your elimination method. Hopefully that jogs your memory enough you can get in and start working with it. Okay, now, when do we need to write out, when do we need two equations? When do we need to satisfy two equations at one time? And there are situations where, and again, I said it before, if there are two things that I don't know, if there are two things that I do not have values for and that I want values for, then I'm going to have two equations to figure that out. So here, Sally has some $1 and $5 bills in her purse. She has a total of 15 bills that are worth $47. So we need to figure out how many 1s and 5s she has. Okay? Here's a situation where there's two things we don't know. We don't know how many 1s she has. We don't know how many 5s she has. So there are two things we don't know, which means we're going to have two variables, an x and a y. In this particular situation, how we define those does not matter. The number of $1 bills in her purse does not influence or is not dependent upon how many $5 bills she has in her purse. She can carry as many 1s as she wants and as many 5s as she wants. Okay? So it doesn't matter how you define your variables. X can be the number of 1s and y be the number of 5s. You can definitely split those, or flip-flop those if you wanted to. So we've got two unknowns. We need two equations. Where are the two equations going to come from? Well, they're going to come from either physically counting the bills, or write an equation based on the worth of those bills. Right? If we're to physically count them up, the x's and the y's, and the number of 1s and the number of 5s, and add those together, then that should give you 15, because she's got 15 bills in her purse. We know that. Now, we also know that the worth of those 15 bills is $47. That's how much it's worth. So how do we get to that $47? Well, we would count the number of $1 bills in her purse and multiply by 1, because that's how much they're worth. And the number of 5s, we'd count those up and multiply those guys by 5, because we know that's how much they're worth. And so there are your two equations. Okay? And we've got to solve that to figure out how many 1s and 5s we are. Now when we solve, we get a value for x and a value for y. We're going to have the number of 1s and the number of 5s. So again, it's up to you which method you use. I wouldn't graph it. It's a terrible method. You're welcome to use substitution. You can always solve one of the equations for one of the variables and then substitute in. But like I said before, I like elimination, and so I'm going to use elimination here. I'm going to multiply the top equation by -1. These guys already have common denominators for coefficients, the 1 and the 1, but I've got to make one of them a negative. So I chose to make the top equation have a -1 coefficient, so we get negative x minus y equals -15. And then when we add the two equations, those x's are going to add out to 0. We get 4y equals 32. Divide both sides by 4, and we get 8. So if y is equal to 8, that means that Sally has 8 5s in her purse. Well, if she has 8 5s in her purse, then, and she has 15 total bills, that means that she must have 7 1s. Just substitute 8 into one of the other two equations and you'll be able to figure that out. So Sally has 7 1s and 8 5s. In her purse. Okay? So there you go. Another situation here. Richard Sporting Goods received a shipment of 124 golf bags. There are two types of golf bags, full-size and collapsible, and we've got the cost of each one. Now, we know that there are 124 total golf bags, and the bill from the supplier was $3,430. So how many full-size bags and how many collapsible bags did Richard Sporting Goods receive? This is a lot like number 11, where we've got to define two variables. We don't know how many full-size and how many collapsible bags they got. So it doesn't matter. Like, it's not like Richard Sporting Goods says that for every 5 collapsible bags we need to carry 1 full-size. So one doesn't depend on the other. So we can make these whatever. X can be the number of full-size, and y can be the number of collapsible. And so again, our first equation will come from counting the golf bags. So x plus y, the number of bags of each, needs to equal 124. Now the cost, 124 golf bags cost Richard Sporting Goods $3,430, right? Well, the way we get that total cost is to find out how much the full-size bags cost us and how much the collapsible bags cost. So to find out the cost of the full-size bags, we take the number of full-size bags, which is x, and multiply by the cost of one of them, which is $38.50. And then we're going to add to that the cost of the collapsible bags, which is the number of bags, y, times the cost, which is $22.50. And now we've got these two equations that we want to work with and find a solution for. Okay? So, I said before, I like to use elimination, but my coefficients here are decimals, and that becomes a little tricky. I certainly could multiply the top equation by negative 22.50, but that is a little bit weird. So, I'm going to go ahead and use substitution here. I'm going to subtract y in this first equation, get x equals 124 minus y, and then substitute that in for the x right there. So we get 3850 times 124 minus y plus 2250y equals 3,430. Okay, and now we need a little help from our handy dandy calculator to solve this out. So we distribute that 3850. We get 4774 minus 3850y plus 2250y equals 3430. Then we combine our like terms. We get 4774 minus 16y equals 3430. Subtract the 4774 from both sides. Having a hard time writing this morning. We get negative 1344. Then divide both sides by negative 16. And we find out that y is 84. Which tells us that there were 84 collapsible bags. If there are 124 bags total, then we can just plug in 84 for y in that first equation and find out that there were 40 full-size bags. We want to write that out into a nice sentence. Richards received 40 full-size bags and 84 collapsible bags. Okay? There you go. All right. Try 13. And see if you can come up with the two equations, okay? Stop the video, you can start it back up, and then see how you did. Okay, so did you define your variables this way and get equations like this? So I'll let x be the number of football cards and y be the number of baseball cards. If you flipped the definition of your variables, which is perfectly fine, then your equations might be a little bit opposite of mine, but I know that if I count the number of football cards and the number of baseball cards and add those two together, I should get 360. That's how many cards he has total. Sorry about that. And then it also says that the number of baseball cards that he has is, so the number of baseball cards is twice as many as the football cards. That's where the 2x came from. Just take the number of football cards times 2. And add, and it's 30 more than that. So we add 30 to that. So that's where the two equations come from. And we're set up for substitution because y is already, the second equation is already solved for y. So I'm not going to force elimination. I'm going to go ahead and substitute 2x plus 30 in for y into that first equation. It's just going to be a little bit easier. So like I said, while I like elimination a lot, I'm not going to force my way into it. And so apparently he has 110 football cards. Well, if he has 110 football cards, then substituting 110 into the first equation, we're going to find out that he has 250 baseball cards. 30 more than twice the number of football cards. Okay? All right, that's it. If you have any questions or if you're still a little confused about what we're doing here, make sure you come in and get some help. Okay? Otherwise, homework's out in Canvas. We'll see you next time.